For experiment 2, we are going to study for a fixed mass of gas to study the relation between the pressure P and temperature T of a gas at constant volume V. The procedures are: first, we connect the setup shown in the diagram. Second, we use a Bunsen frame to heat up the water bath and use the stirrer to stir the water regularly. Third, we use the thermometer to measure the temperature T of the gas inside the conical flask. And we use the Bourdon gauge to measure the corresponding gas pressure inside the conical flask P at regular time interval. Let's look at some precautions needed. 要注意嘅嘢。First is the position of the thermometer. The thermometer should not touch the bottom of the beaker. Next is to maintain fixed mass of gas. In order to prevent leakage of gas, we should lubricate all the junctions with oil. The third thing is the position of the flask. The flask should be totally immersed in water. Next, let's see the improvement in the experiment to make the result more accurate. The first thing is, why should we use short rubber tubing? The reason is that for short rubber tubing, the volume of the gas inside the tubing is negligible. That means the pressure due to the gas inside the tubing is also negligible. The second thing is the function of the stirrer. It is used to stir the water to ensure that the water temperature is uniform. The next thing is to use thin-walled flasks. Thin-walled glass is used so that the heat transfer from the hot water to the air inside the flask is very fast. Therefore, the water temperature is almost equal to the temperature of the gas inside at the same time. This increases the sensitivity 靈敏度 of the experiment. If we have 4 sets of data 1, 2, 3, 4, the corresponding value T1 P1, T2 P2, T3 P3, T4 P4 are plotted on the graph of pressure against temperature in degrees Celsius. They all lie on a straight line, and we connect the 4 points, and if we extend the line backward, it will pass through the temperature axis at a temperature equal to -273 degrees Celsius if the experiment is done very accurately. Then we say the gas pressure varies linearly with temperature T in degrees Celsius. Now we convert the temperature in degrees Celsius to temperature in Kelvin temperature. By the conversion, Tk Kelvin temperature equal to degrees Celsius temperature plus 273. Then the temperature axis will change from T in degrees Celsius to T in K, and this point becomes 0K, and this point becomes 273K. we move the pressure axis to the 0K point, then we have the new graph. If we plot the graph of P against temperature T in Kelvin temperature, then we will have a straight line passing through the origin. In this case, we say the pressure of the gas is proportional to temperature in Kelvin temperature. Or for these points 1, 2, 3, 4. When the temperature scale is in Kelvin temperature, then we have the pressure over the temperature is equal to a constant. That is, we have P1 over T1 equal to P2 over T2 equal to P3 over T3 equal to P4 over T4, etc. Notice that the temperature 0K is called absolute zero, 絕對零度, because at this temperature the pressure of the gas becomes zero. Therefore, absolute zero, 0K, is the lowest temperature in the world. 最細嘅溫度，冇溫度可以低得過呢個㗎啦。Absolute temperature Tk equal to Celsius temperature Tc plus 273. This is very important. You must remember this one. Using the conversion Tk equal to Tc plus 273 and Tc equal to Tk minus 273 to complete the table in question number 1 and number 2. The results are 2, 4, 3, 2, 6, 3, 2, 7, 3, 3, 2, 3, 3, 7, 3, and negative 2, 7, 3, negative 2, 2, 3, negative 73, 0, 3, 3, 2, 7. First, spend some time to read question number 3. For part A, in order to ensure the temperature inside the flask, that is the gas temperature, is equal to the water temperature, we should, before taking the reading, switch off the heater and then stir the water. For part B, part 1, since P varies linearly with temperature in degrees Celsius, the graph is a straight line. Therefore, P minus 1.21 over T minus 80 equal to 1.21 minus 1.02 over 80 minus 33. The equation is P equal to 0.004 T plus 0.89. For part 2, when temperature of the gas is 65 degrees Celsius, we have the pressure equal to 0.004 times 65 plus 0.89, which is equal to 1.15 times 10 to the power 5 Pascal. For part 3, the absolute zero temperature from the graph is this point. We call this T0. At this point, the pressure of the gas is equal to 0. Therefore, we substitute 0 into the P reading. We have 0 equal to 0.004 times T naught plus 0.89. Therefore, we have the absolute zero temperature from this experiment equal to negative 223 degrees Celsius. Notice that the experimental result for absolute zero may not be equal to negative 273 degrees Celsius, which are the standard value. First, spend some time to read question number 4 and number 5. For question number 4, when volume of the container is constant, the distance between the gas molecule and the container wall will remain unchanged. When the temperature of the gas is increased, the airflow speed of the gas molecule will increase. Or the gas molecule will hit the container wall more violently and more frequently. Therefore, the gas pressure will increase. For part A, if the fire extinguisher is exposed under sunlight, the pressure of the gas inside will increase. If the pressure exceeds the maximum allowable pressure, then explosion will occur. For part B, since the volume of the fire extinguisher is constant, we apply the law P1 over T1 equal to P2 over T2. We have 2 times 10 to the power 7 over 20 plus 273 equal to P2 over 90 degree plus 273, imply P2 equal to 2.48 times 10 to the power 7 PA, which is smaller than 2.5 times 10 to the power 7 PA. Therefore, will not explode. Take a few minutes to read question number 6 and 7 first. For question number 6, since it is a sealed metal box, therefore the volume can be considered as a constant value. We use this law P1 over T1 equal to P2 over T2. Remember, the temperature T1, T2 should be the absolute temperature. Therefore, 1.2 times 10 to the power 5 over 30 plus 273 equal to P2 over negative 30 plus 273. The new pressure will be P2 equal to 0.962 times 10 to the power 5 Pascal. For question number 7, we have T1 equal to 22 degrees Celsius and the P1 1.1 times 10 to the power 5, T2 35 degrees Celsius. We have the equation for part A, P1 over T1 equal to P2 over T2. Remember to convert the temperature T into Kelvin temperature, absolute temperature, that is, we have 1.1 times 10 to the power 5 over 22 plus 273 equal to P2 over 35 plus 273, implying that P2 equal to 1.15 times 10 to the power 5 Pascal. The assumption for this law is that we assume the volume of the tire is constant and there is no leakage of gas. That means we have a fixed mass of air inside the tire.